Let's answer the first question first, about structural small worlds. Let's use symbol L to denote the median of shortest path between node pairs. So if I got node pair ij, and the shortest path distance between them is dij, and then I look at all the node pairs and the corresponding shortest path distance, histogram it, and then I get L as the median. And I want L to be small. Now, of course, L will be small if there are only a few nodes. So really I want to say L is small relative to the number of nodes, say n. And more precisely, I want L to grow like a slow function of the number of nodes. How slow? For example, logarithmic function. Then even for exponential growth, after taking the log, it becomes just linear. So what we now want to do is to reverse engineer, and we will comment on this, the utility and pitfalls of reverse engineering, topology or functionality of a network towards the end of the lecture. We want to reverse engineer and build an explanatory model to explain the observation, like what physicists would do, to explain that observation, this time about the social network, that L is often a slow function of the number of nodes. But whatever explanatory model we have, it can be just a tree growing like this, 20 to the power 6. Because we know that violates another observation empirically made in social network. That is, there's a lot of transitivity, quantified, for example, by clustering coefficient of a graph, quantifying the degree of existence of triad closures. And we're going to use C to denote this metric clustering coefficient. I just want to highlight C, clustering coefficient of a graph, has nothing to do with the cluster density P that we talked about in the last lecture in contagion model. Okay, clustering coefficient of a graph is not the the density of a subset of nodes. So what is clustering coefficient? Remember, we're trying to quantify the following observation, that in many social networks, if A, B, C forms a connected triple like this, then there's a good chance that it also closes the triangle. Okay, that's why it's called triad closure. So we want to look at the number of triangles versus the number of connected triples. And we want this metric to be normalized, so it always lies between 0 and 1 for all graphs. In particular, if it is a triangle, then we want C to be 1. In order to accomplish this normalization, we're going to divide the number of connect triples by 3. Why? Because of different ways we count connected triples versus we count a number of triangles. If there is a link here, then the triangle exists. We call that a triangle ABC. We count it only once. But when we count a number of connected triples, we actually have to count AB and BC. Two links coexist, then there's this connected triple, whether there's a link AC or not. If there is one, we also have a triangle. If not, we don't. But for connected triple, this is one connected triple. And then we can also write AC and CB, two links, that is another connected triple. And BA link and AC link, that's another connected triple. So just because when we count connected triples, we count basically 3 times. So we divide it by 3 to take into account that overcounting, and therefore now C will be guaranteed to lie within 0 and 1. For just a triangle, it will be 1. For just a connected triple, which is a line here, it will be 0. Now the question for a bigger general graph, what will C look like? We want C to be big and L to be small for our explanatory model. So here's another graph, slightly bigger, 4 nodes and 4 links. Let's see, what is the clustering coefficient for triad closure in this graph? Well, for this graph, this number C is actually easy to compute, right? C equals the number of triangle over the number of connected triples over 3. How many triangles are there? Well, there's only one triangle. Okay, 1 to 3 nodes is triangle. What about connected triples here? Well, there are, let's see how many connected triples. 2, 1, 3. That's a connected triple. Okay, 1, 2, 3. That's another connected triple. 1, 3, 2. That's another connected triple. 1, 2, 4. That's another connected triple. And 3, 2, 4. That's another connected triple. So there are actually 5 connected triples. Of course, some of them we basically counted more than once. So we have the normalization divided by 3. And that means the clustering coefficient of this graph is 3/5, which is a pretty big number, considering that C must lie within 0 and 1. Okay. And that satisfies our intuition, because in this graph we can see that it is reasonably triad closed. All right, so what kind of model can give us what we want? Big C, small l. First attempt, let's think about a random graph, also called Poisson random graph, also called Erdős-Rényi model of a graph. This is actually heavily studied and has uses in a variety of subjects, but we will actually not talk about random graph except this slide, because of what we want to do in this course. Random graph is neither an accurate depiction of reality nor a useful design tool. But let's still look at this failed attempt to explain small world using random graphs. Random graph, what is that? It's just that given a set of n nodes, look at the possible links, and then they will pop up with a probability p. You throw a coin, loaded coin, probability p. If it shows up heads, then the link exists, otherwise it doesn't. So this is a probabilistic quantity. And let's look at, if you indeed construct such a graph, what would be the L and C? Now L is actually small, as you can intuitively see. Okay, because between any node pairs, there's a chance of P that they are directly connected. But the clustering coefficient C is also small. When we look at C now, we're talking about expected C and expected L, because this is a probabilistic object. Now, without going into the details there, it suffices to show the intuition that C for a Poisson random graph is the following. Small c over n minus 1. N is the number of nodes. Small c is the expected degree of a node. Why is that? Why is this the expression for the expected clustering coefficient big C for a random graph? Well, because the chance, the probability that two nodes are connected is C over n minus 1 in a random graph. Okay, this is how many connections you have, and this is how many nodes are out there other than yourself, and therefore their ratio is the expected a number, the probability of the two nodes being connected, independent of whether these two nodes are already indirectly connected by another node or not. Doesn't matter. That's not how the graph was constructed. So the chance that these two nodes are connected is exactly just C over n minus 1. So suppose we look at a graph with, say, 100 million people, and each has 1,000 friends. That's a lot already, much bigger than Dunbar's number. Still, the clustering coefficient is only on the order of 10 to the minus 3, which is way too small. We know C will be much bigger than that, orders of magnitude bigger than that in a real social network. So random graph can explain small l, but not big C. What about the extreme end on the other hand? A regular graph, let's say a regular ring graph. What's a regular ring graph? Let's draw a ring here. Okay, it's just a line with two ends connected. and let's say there are nodes living here. Okay, in this case there are 8 nodes, so n equals 8. Just like a random graph is parameterized by a number p, that's the probability of a link appearing or not, a regular ring graph is parameterized by a number c, a small c. Now this small c is not exactly what we just used, expected degree. Here is the actual deterministic degree c here. Okay, that's the number of neighbors each node has, is the degree of each node. Given this is a regular graph, you can rotate however you want, it still looks the same. This is basically the degree for all the nodes. Now in this particular ring graph, c is 2, because for each node there are 2 neighbors. The degree is 2 for everyone. I can add a few more. Say let's make a c an even number. I can also connect to this node with 2 hop neighbors now. So there's a direct link going out over there now. Okay. Similarly, I'll add all these. Now in this case, c is no longer 2, c is 4, because there's one more missing. Okay. Because every node actually has 4 neighbors. I pick this node, 1 neighbor, 2 neighbor, 3 neighbor, 4 neighbor. Okay, don't worry too much about exactly the way the lines are drawn. You can easily count that 1, 2, 3, 4. This node has 4 neighbors and is symmetric, it's regular. So every node has 4 neighbors, degree 4 and 8 nodes. Of course, you can make C even bigger now. Okay. If we insist the C to be even, then you can make C to be 6 and eventually 6C be 8. That will be a so-called full mesh network. Every node is connected to every other node. In fact, in this case, because of even number of nodes here, you can't even do that. The largest an even C you can get is just 6. Okay. Oh well, so in this case, what would be C and what would be L? First of all, C is now much better. Okay, let's compute the clustering coefficient here, C. Number of triangles and number of connected triples. Turns out number of connected triples is easy to compute. If you just look at each node, because it's symmetric, we can just count those centered around each individual node. The number of connected triples is easy to choose. Count is just C choose 2. Okay, you've got C neighbors, and you choose 2 of them, then you form a connected triple. It might be a triangle, might not be a triangle, but still, number of connected triples centered around a node is just C over C choose 2. Of course, don't forget you have to divide by 3 for normalization. Now, what about the number of triangles centered around a given node? Let's think about that. Well, first, to form a triangle, you need to go out, right? 1 step, then you need to go out another step, then you have to come back. Otherwise, you don't close it. You don't have a triangle. So you have to go 2 steps out and then be able to come back in one shot. So how many of such choices there are? Well, in order to be able to come back in one hop, you can only go out C over 2 that far. Farther than that, you won't be able to come back. And out of those, you can choose 2 because you'll be making 2 steps. So the number of triangles is C over 2 choose 2. And the number of connected triples is C over 2. What is this expression? It is half C over 2 times C over 2 minus 1 divided by half C minus 1 over 3, which simplifies to 3 times C minus 2 over 4 times C minus 1. This is the clustering coefficient quantifying triad enclosure on a regular ring graph. You can see that the number of nodes doesn't come into play here because this is entirely symmetric. So only C matters. The deterministic number, the degree here for each node matters. Well, for sanity check, let's see what happens if C is 2. Well, we know if C is 2, we're just talking about a ring. There is no triangle. There's only connected triple. Indeed, when C is 2, this becomes 0, as you can see. Okay, so triad closure doesn't exist. Clustering coefficient big C is 0. What if C is 4 now? Like this graph. Actually, the way we draw this is hard to see. Intuitively, what should the clustering coefficient be? Here's another way to draw the same graph, which is you can easily verify for yourself like this. These are the nodes. And now you can clearly see the clustering coefficient should be half, because had I also drawn these dotted lines, which don't actually exist here, I would have actually triad closure, all the triad closures. But they don't exist, only these parts exist. So intuitively, this way of drawing this same picture shows that clustering coefficient should be half. And indeed, if you plug in C equals 4 here, what you get is that clustering coefficient is 1/2. Okay. Now, what if C becomes real big, like this small c? Okay. When this little c is like infinite, then what would happen? Well, then in that case, this simplifies this to 3/4. In other words, for regular ring graph, the clustering coefficient can only go up to 3/4, but that's already very, very big. Compared to, say, 10 to the minus 3 for our Poisson random graph, this is way bigger. And indeed, most likely it would be at least 4, and therefore a clustering coefficient is between half and 3/4. It's a small dynamic range, but it is of the right magnitude. Good. We got C checked off. Okay, we get a large C on a regular ring graph, which is not too surprising because with enough C, you quickly start closing the triangles. Now the question is, what about these L's? That's where the problem is with a regular ring graph. To explain small world, it doesn't have a very small L. Indeed, if you want to go from this node to that node, you actually have to at least hop through here and here. But remember, this is only a network with 8 nodes. When you have many more nodes, n is big on a regular ring, then no matter how many C you add, for quite a large range of degrees, you still need to hop slowly locally. You do not have a direct long-range link anywhere in this graph. This graph only got short-range links. Okay, so with only short-range links, you cannot possibly have a small L. So here's the problem. Random graph got small l, very good, but also small c, not good. Regular, say, ring graph got a large clustering coefficient c, very good, but also large l, not so good. We want a large c like regular graph, but a small l like a random graph. So maybe a hybrid. How about we combine these two ideas together? Start with a regular graph, but then add some random links. And that's precisely the Watt-Strogas model that explains small world.